This is a gas law constant lab, and I'm just going to bring up a screen share, and we are going to look at the pre-lab for this. Grab a little marker here, and here we go. We are going to be trying to determine the gas law constant R. Now, we know what that is, but we are going to try to verify it with our own data instead of just being able to pull it off of a table and say, this is what R is. So in other words, we're going to have to do an experiment, and we're going to react some magnesium and hydrochloric acid to form some hydrogen gas. And we're going to know the pressure this is at. It's a direct measurement using a barometer. We're going to actually collect hydrogen gas in a big long tube called a eudiometer, or a gas collecting tube, and we're going to measure that volume. We're going to figure out the number of moles by reacting some magnesium, all of it in hydrochloric acid, and then projecting how much hydrogen gas that should produce using the mole train. R is what we're trying to find out, and then we're just going to use a thermometer to record the temperature. So we're going to know P, V, N, and T, some with direct measurements, some with indirect measurements. But if we know all four of those things, then we can determine R for our experiment. And that's what the plan is. Okay. Here's a table here with some vapor pressures for water. We're going to come back to that in some point. So you're going to be seeing that. And let's see, I'm going to go right to the pre-lab questions right here. So first question says, answer the following questions, show work calculations. And you can look at page 2 of your homework packet, and I think it should be pretty clear that the gas law constant R is supposed to be 0.0821 liter atmospheres per mole K, or 62.4 liters millimeters mercury per mole K. Okay, and we'll probably focus on the second one in this lab. That's where the calculations lead us in our target right here. It says, write a balanced equation for the chemical reaction in the lab. If you look, there's some magnesium, which is encaged in copper, but copper is below hydrochloric acid on the activity series and won't react. Magnesium is above hydrochloric acid on the activity series. So what do we have? We have a replacement of magnesium replacing hydrogen in this reaction, forming magnesium chloride, and then hydrogen gas right here. So yes, this is a single replacement or single displacement reaction. So, and I think we've also answered question number 4. Just look at the subscripts in the equation above. Okay, question number 5 is a little bit interesting. It says hydrogen gas is collected over water in a gas collecting tube. The partial pressure of hydrogen gas is 760 millimeters mercury, and the partial pressure of water is 70 millimeters mercury. What is the total pressure? So first off, maybe we should just go through a little diagram of what this experiment will look like. And you're going to have some water here, and then you're going to have a tube that's all filled with water. But the magnesium is going to react with hydrochloric acid drips down, okay? And so this is all water. There might be some hydrochloric acid, but there's no gas in this tube to start, and this is all water right here. Well, guess what happens? The hydrochloric acid drips down, meets the magnesium, it reacts, it creates bubbles. There's a little hole for the gas, for the water to escape out, and then gas goes up in the tube. And it's virtually all hydrogen gas, okay? But does water evaporate? Absolutely. The higher the temperature, the more it evaporates. So we have to account for that little bit of water vapor that evaporates, as well as the hydrogen gas, which is going to be most of the stuff that we collect. So to do that, we're going to make an adjustment using Dalton's law of partial pressures, which just says the total pressure of a gas is the sum of all the partial pressures available, whether it's 2 things or 3 things or 4 gases or 5 gases or so on. And in our lab, what's going to happen is, I'm just going to move this forward a little bit, is it's going to be just the pressure of hydrogen and water vapor. Now, looking at this question, it says the partial pressure of hydrogen, and the hydrogen is going to be a lot bigger than the pressure of the water vapor when we do the lab. And it looks like it is in this one. So if you're thinking, oh, the pressure of the hydrogen is 700, the pressure of the water vapor is 70, what am I going to do? Add those two things. That's exactly right. So just add up 770, and that's going to be your total pressure. Ultimately, when we do the lab, that'll be the same as it should balance with the barometric pressure or the room pressure we have that day. Okay, the final thing is the number of moles of hydrogen gas or liters of hydrogen gas, I guess, is a little bit tricky. And we're going to look at this. This is just an equation working with the mole train and looking back at the equation that we have before. So I'm just going to slide this back up here. And you have this equation right here. And then it says if 0.0400 grams of magnesium completely reacts with excess hydrochloric acid, what volume of hydrogen gas can be produced? So if you know grams of magnesium and you know what there's excess HCl, so all the magnesium reacts just like it's going to happen in your experiment, you can convert grams of magnesium to moles of magnesium by using your mole train. Then you got to go through your mole ratio to figure out moles of magnesium to moles of H2, which looks like a invisible one here and invisible one here, a 1-to-1 ratio. So that'll get you to moles of H2. And then if you're at STP, remember there's 22.4 liters per mole. So you can just go from moles of H2 to liters of H2 by going through the 22.4. Okay, so that is the pre-lab that you should be working on and doing. These were just some hints. Let me know if you have questions. And there is going to be a video with a procedure where you can actually see that, which would be helpful to watch and see what that looks like before doing the lab. Okay, thank you for watching.